Hello, we are the group number 2, made up of the members shown on the screen, and we're going to present the final project of Power System 1, which consists in the study of the power flow of the Roy-Billington transmission system. Although from now on we will refer to it as RBTS. My name is Adrian Jimenez, and I will talk a little bit about the project guideline. On the screen is presented the schematic diagram to be studied. In addition, it is mentioned that bus 1 will be our slot bar with a base voltage of 230 kV, and bus 2 is composed of a PB bar. We will know more about these terms that I'm using later in the presentation. Also, we will work under full load conditions and a power factor of 0.95. We were given all the data referring to the parameters of each of the lines, with the exception of line 9, whose parameters we must calculate. It is necessary to know the injected power, demanded power, and lost powers in the buses and lines. Also, voltages in buses and line currents. To do this, we will use iterative methods, specifically the Gauss-Seidel method using MATLAB software. In addition, we will make comparisons with the DC power flow method and a simulation in a program called PowerWorld. Although we are not given the information of line 9, we are provided with the configuration of it and the type of conductor, and also the length of the line, which is 1000 kilometers. To model this line, we need to calculate its serial and parallel parameters. Resistance, it is defined as a measure of the opposition of the current. The higher this value, the lower the current passing through a conductor with a given voltage is. This relation is determined by the Ohm's law. The image shows a way to visualize it. This is the first serial parameter. Another serial parameter that we're going to calculate is inductance. The inductance is the property of a conductor that opposes changes in electric current. Knowing this value is vital for transmission line modeling. And finally, the parallel parameter of our interest will be the capacitance. Capacitance occurs when there is a potential difference between 2 points. As there is a difference in power between each of the conductors, and in addition, as specified in the project guideline, we also consider the earth effect, there is a potential difference between the conductors and the earth. With these three factors, which will depend on the material used, in this case the Falcom conductor that is created from aluminum, we can obtain this data. As these parameters will depend on the distance of the conductors from each other and from the ground, as you can see, we use expressions that calculate these parameters based on the GMD, geometric medium distance, and the GMR, geometric mean radius.
Hello, my name is Saskia Velarde and I will talk about the transmission line operations. In transmission line operations, we model the line as a two-port network to define the voltages and currents at both ends. For longer distances, it's essential to account for the distributed effects of capacitance and inductance as they significantly influence the line's electrical behavior. What electrical parameters we calculate? The provided code calculates the DC and AC resistance of the transmission line, considering factors like the skin effect and temperature. Inductance is calculated using the formula previously discussed, and the same for the capacitance, and this one is determined while considering the ground effect, which is crucial for analyzing high voltage lines. Circle diagram for the transmission line at the reception end. What is the concept about that? This one is a graphical tool that visualizes the operation of the transmission line at the receiving end, showing how active and reactive power vary along the line. What is the operating point? This one is where the voltages and currents along the line balance under specific load conditions. This point is critical for assessing system stability. On the circle diagram, the operating point is marked where active and reactive powers balance, allowing for an analysis of the line's performance. In the code implementations, this performs detailed calculations to generate the diagram components like the magnitude and angle of the SR phasor between sending and receiving ends. The diagram plotted in MATLAB shows the maximum active and reactive powers, helping us visualize the line's operation point.
My name is Aldo, and I am going to talk about the matrix representation of power system. A bus matrix is a mathematical representation that describes the relationship between the nodes or buses in the network. This matrix is used to simplify and analyze the behavior of the electrical system. This matrix contains the admittances of the branch, and it is used in chart logs analyze and determine voltages and currents. As we can see, we have a matrix where the diagonal elements are the sum of the admittances connected in each bus, and the off-diagonal elements are the negative of the sum of the admittances connected between the buses. From the matrix, we can determine the conductance matrix, that is the real part of this admittance matrix, and also we can determine the substance matrix, that is the imaginary part of this matrix. The method that we use is Gauss-Seidel. First, we have to identify the type of buses that we have in the power system. So the first one is slack, that is unique across the system, and we know the voltage and angle. The second one is the load bus, that we know the real power and reactive power. And the last one is the control voltage bus, that we know the real power and the voltage. Gauss-Seidel method is used to iterate and find the voltage on each bus in the network. Each iteration updates the bus voltage estimated based on network conditions until the solution converts to a state where the differences between iterations are minimal. So we use this equation to resolve the problem, and later we will present the results.
Hi, my name is Hamilton Alavera, and in this section we will compare the data obtained theoretically, the code in MATLAB, and we will compare it with the simulation made in the PowerWorld simulator software. So first, let's start by obtaining JBus of the system. This matrix represents the admittance of the electrical system. And as you can see, the data obtained are the following. So first, we calculate all the matrix, admittance matrix, conductance matrix, and impedance matrix. Then, using the Gauss-Seidel method, we will find the voltage in each bar, as you can see. This is the voltage in each bar. From here, we can find the current, the current values in each branch, as well as injected current and the power in each bar. So, this is the current injected in each bar. This is the power injected in each bar. This is the total power losses. So now I will show you the system made in the simulator. So as you can see, it has 6 buses, 9 lines, slack bus, PV bus, and 5 loads. So let's start comparing the values obtained in the MATLAB code with the simulator. So to show the J bus, you go to case information, then solution details, and then to J bus. As you can see, the values obtained in the simulator are the same values obtained in the MATLAB code. Then we want to obtain the voltage values and the angles obtained in each bars in per unit. So we go to room move. We go to room move. Then we go to tools. We reset the simulator and run the simulator. As you can see, the values obtained, as you can see, there are the values obtained in each bar of the system. And if we compare these values with the values obtained in the MATLAB code, you can see that they are the same.
Hello, my name is Ivan Barrales, and I will describe the comparison made between the Gauss-Seidel method and the non-iterative DC power flow method. Okay, the DC flow method assumes that the reactive power is negligible, which is valid in systems where the reactive power is much smaller than the active power. However, when reactive power is significant, as in this case, the DC flow method can generate considerable errors. In this comparison, it is observed that the active powers in the methods are similar in some cases, but in others, the differences are more noticeable. This is because the DC method does not consider the imaginary part, which affects the accuracy. On lines such as P13 and P12, the active power values between the two methods are relatively close, indicating that the DC flux approximation is reasonable for those lines. However, in lines such as P35 and P60, 56, the difference or longer, showing that the omission of reactive power in the DC methods leads to significant errors when reactive power is not negligible. For the conclusions, the estimation by network of support of a line was used to calculate the parameters of transmission line 9 to make the operating circle diagram of the line and after the operation point. And modeling the long transmission line using two-port networks was crucial to understand system behavior and ensure power flow stability. Thank you.